All right, let's get going. Um, Precious mineral systems. And this is based on Mulligroves and Santosh, chapter 8. So when I started looking at this, I go, oh, precious minerals, precious metals. That will be platinum group elements and silver and gold. It's like, no, it's just gold. That's all they want to talk about, which is, as you'll see, it's a pretty long lecture. It'll probably take us the whole 2 hours and 45 minutes. So, but you guys know, chime in when you got a question. The questions are the best part of this class, to be honest with you. Um, so there we go. You don't win a silver medal, you lose a gold medal. I'm not sure why I thought that was funny. It seems kind of dark, but okay.
It's pretty
What
funny.
is what is a precious metal? So I looked that up after I saw what was in the chapter, and I went to the Oxford Dictionary and said, "What's a precious metal?" And they said, "Gold, silver, and platinum." Okay, that seems more inclusive than just gold. And then Wikipedia, I went to Wikipedia. Precious metals are rare, naturally occurring metals of high economic value. Gold was $4,200 an ounce last week. I'm not sure what it is, but it seems to just keep going up. Precious metals, particularly the noble metals, are more stable and less chemically affected than most other elements. In their elemental form, they are usually ductile and lustrous, and especially gold and other precious metals like platinum, they do occur in their native state. So they were easy to identify early. They just stand out. So historically, precious metals were important as money, but they are now regarded mainly as investment in industrial raw materials. So, another word that people use is sometimes called the noble metals. So the noble metals are shown here in green. So there's 7 that are usually identified, ruthenium, rhodium, palladium, osmium, iridium, platinum, and gold. So that's the PGEs plus gold. And then sometimes silver is included there. And sometimes mercury and copper included, although I don't really understand that. So then there's 6 others that are considered noble metals in a limited sense: technetium and rhenium, plus arsenic, antimony, bismuth, and polonium. I don't understand how they're lumping those together with the noble metals, but that's what I found. So the thick black line encloses the 7 to 8 metals most often recognized as noble metals, with people just not sure what to do with silver. And the thing about silver is it's often not included because it has a much greater reactivity. You see a lot more silver compounds than you do these other 7 noble metals. So we'll just leave that.
Precious metals are elemental metals that have high economic value. In some cases, the metals have been used as currency. In other cases, the metal is precious because it is valued for other uses and is rare. The most widely known precious metals are corrosion resistant and used in jewelry, currency, and investments. Gold, the most well-known precious metal in the world. Gold is the easiest precious metal to recognize because of its unique yellow color. Gold is popular because of its color, malleability, and conductivity. Gold remains a popular investment option as it hedges against inflation. Highly conductive, it resists corrosion. Many electronic devices use gold in different components. Some dentists use gold in their tools. Different metals mixed with gold to make it stronger. This changes the purity of the gold. Naturally, the purer the gold, the more valuable it is. The carat of gold describes its purity. 24 karat, 99.9% gold, the purest form, and so on. 1 ounce of gold values at $2,526.82 according to silverprice.org. Uses jewelry, electronics, radiation shielding, thermal insulation. It comes from mines primarily in China, Australia, the United States, and South Africa. Silver. Silver has been a precious, valued metal since ancient times. Pure silver has a white hue. A softer metal, it was once considered more valuable than gold. Silver is a popular precious metal for jewelry. It has utility in decoration, eating utensils, and electronics, but its value extends well beyond all of this. It has the highest electrical and thermal conductivity of all the elements and has the lowest contact resistance. Like gold, silver must combine with another alloy to become stronger. Copper is a common choice. 1 ounce of silver values at $28.83, according to silverprice.org, uses jewelry, coins, batteries, electronics, dentistry, antimicrobial agents, photography. Major sources are Peru, Mexico, Chile, China. Platinum. Platinum is a dense, malleable metal with exceptional corrosion resistance. It is nearly 15 times rarer than gold and finds uses in a wide range of areas. This combination of rarity and functionality might make platinum the most precious metal. The dense metal can be easily formed and manipulated, yet it retains its durability. It resists wear and tear, which makes it an essential component to industrial manufacturing. It mixes well with other metal alloys. Being scratch-resistant also adds to platinum's value and utility. Uses catalysts, jewelry, weaponry, dentistry. Major sources are South Africa, Canada, Russia. Palladium. Palladium is similar to platinum in its properties. Like platinum, this element can absorb an enormous quantity of hydrogen. It is a rare malleable metal, able to maintain stability at high temperatures. This feature makes it valuable to car manufacturers. Putting it in cars helps their emissions go down. 1 ounce of palladium values at $1,083.90, according to AppMex. Uses white gold jewelry, catalytic converters in automobiles, electrode plating in electronics. Major sources: Russia, Canada, United States, South Africa. Ruthenium. Ruthenium is one of the platinum group metals, or PGMs. All metals of this element family are considered precious metals because they are typically found together in nature and share similar properties. It can also make palladium stronger when added as an alloy. The electronics industry uses ruthenium in plating electric contacts. The alloy's hardiness makes it a popular choice for combining essential parts together. It resists wear far better than many metals. It is another rare metal and can rarely be found in the earth, especially combined with other elements. Ruthenium values at $265 per troy ounce, according to Infomine. Uses: increasing hardness in alloys and coating electrical contacts to improve durability and corrosion resistance. Major sources: Russia, North America, South America. Rhodium. This highly reflective metal is extremely valuable due to its rarity in the world. It tolerates corrosive objects without warping or changing. Rhodium also has a high melting point, meaning it takes a long time for it to reach a boiling point where the metal becomes liquid. Uses: reflectivity, including jewelry, mirrors, and other reflectors, and automotive uses. Russia, South Africa, and Canada are the largest producers in the world. Iridium. A white-like metal, iridium is a byproduct of nickel mining. It is processed from the platinum ore. Although it is part of the platinum family, it is on the extreme end. This is because it has an extremely high melting point and considered dense. In fact, it is the second densest metal on Earth. Iridium is extremely brittle, yet considered the most corrosion-resistant metal. The metal comes from meteorites that exist in the Earth's crust. Infomine puts iridium's price at $1,460 per troy ounce. Uses: pen nibs, watches, jewelry, compasses, electronics, medicine, automotive industry. Major source: South Africa. Osmium. Osmium is arguably tied with iridium as the element with the highest density. This bluish metal is extremely hard and brittle, with a high melting point. While it's too heavy and brittle to use in jewelry and gives off an unpleasant odor, this precious metal is a desirable addition when making alloys. Osmium sells for around $1,000 per troy ounce. Uses pen nibs, electrical contacts, hardening platinum alloys. Major sources: Russia, North America, South America. Other precious metals. Other elements are sometimes considered to be precious metals. Rhenium is commonly included on the list. Some sources consider indium to be a precious metal. Alloys made using precious metals are themselves precious. A good example is electrum, a naturally occurring alloy of silver and gold. Copper. Copper sometimes is listed as a precious metal because it is used in currency and jewelry. But copper is plentiful and readily oxidizes in moist air, so it is not particularly common to see it considered precious.
So I just thought we'd, just in case anybody didn't notice what gold was doing. So here we are back in 21, 22, 23, $2,000 an ounce or less. 24 pokes its head above $2,000 an ounce. And it has just been rising and rising and rising. So, a little over a week ago, it was $4,250 an ounce, which is more than double what it was 2 or 3 years ago. So you can imagine that there's a lot of people interested in gold.
It's just so you know, it's $4,000 even right now.
Oh, it went down, huh?
Mhm.
Good time to buy. Well, anyway, in Muller et al., the chapter, Precious Metals, is about gold. So you can say, well, wait, that's a little bit of false advertising. But the one thing everybody can agree on is that gold is a precious metal, and these other, elements we can argue about. But there are 9 sections in that chapter, 48 pages. There it starts with the introduction, then orogenic gold systems, intrusion-related gold systems, Carlin-type gold systems, gold-rich submarine porphyry epithermal VMSs, which is a section we've moved to the submarine mining and mineral deposits and mining lecture, but it's hydrothermal, Then there's high sulfidation epithermal gold systems, low sulfidation epithermal gold systems, placer gold systems, and placer gold systems. So when you say gold is where you find it, it's like, yeah, that is definitely true. It is a very, very wide range of mineralizing systems. So John, you're asking how many mineralizing systems are there? So here we have one element, and it looks like there's 9 systems, the way the book's defining it. All right, so the distribution of different types of known gold deposits over geologic time. There's, we're going back in time from today, the Cenozoic, the Mesozoic, the Paleozoic, the Neoproterozoic, the Mesoproterozoic, the Paleoproterozoic, the Neoarchean, the Mesoarchean. And you can see this story that we've alluded to previously, that, in these old rocks, there's a lot of minerals. So look at all of the gold there. This is mostly the Witwatersrand, which we'll talk about when we get to paleoplacers. But you'll notice there's a lot in the Cenozoic. And I think this might be skewed because there's a lot more Neoproterozoic gold, especially in Northeast Africa. That's become a pretty hot area for gold exploration and mining now. But anyway, the gold deposits are distributed different, heterogeneously through time. We'll talk about that in the next lecture. All right, so here is a pie diagram showing the world's leading gold producers as of 2016. It's changed a bit, but not that much. Here is China, as always, leading the pack. Australia, Russia, the United States, Canada, Peru, South America, Mexico, Uzbekistan, Indonesia, Ghana, Brazil, Papua New Guinea. Now, in the United States, the interesting thing is what's happening in Nevada. So here we are, Nevada. Well, that's about the time that Europeans started poking into Nevada. So, the 49ers, some of them spilled over. And then this is all the United States, right? So this is California. We'll be talking about that later. And then when they discovered the Homestake mine in South Dakota, it went up. And what you're seeing here in the dark orange is what's coming out of Nevada. And look what starts to happen around 1985. U.S. gold production was declining, and then it just skyrockets. This almost reminds me of the Permian Basin oil production, and it's all coming out of Nevada, right? The gold, I mean, there's still some gold coming out of Homestake and other places in the United States, but the doubling and doubling and doubling again of U.S. gold production is ultimately related to what's happened in the last, 40 years in Nevada. We're going to talk more about that because that's the Carlin trend. We talk about the Carlin trend later. All right. So in the introduction, the book puts in this kind of interesting diagram showing the different tectonics of gold deposits that get discussed. So high sulfur. So you can see they've got subduction zones and, interesting relationship between the thickness of the continental crust and the subcontinental atmospheric mantle, which, cartoons generally don't pay attention to scale, but you can see the different tectonic environments that these gold deposits are forming in. The key point is that implicit in gold mineralization is plate tectonics. So we don't know if there's plate tectonics in the Mesoarchean, but we know there's plate tectonics going on now, and we see quite a bit of different kinds of gold deposits that have formed over the last few 100 million years. And here they are. So we're going to go over each of these, just this sort of an overview kind of thing. So the gold deposits are very complex, 3 groups and 11 subgroups. So it's like, okay, I'm confused already, and you just started the lecture. So it's like, okay, well, that's where we are. So this is at depth in the crust, 0 down to 10 kilometers. This is where they form, not where we mine them, although we will find out about, mines that go down to 10 kilometers in South Africa, all sorts of complicated stuff. So I guess that's by way of just getting you ready to get confused so that you're not frustrated when you get confused, but in fact, understand that this is a confusing story. All right. And your book goes into what they call orogenic gold systems. And these are kind of a hydrothermal mineralizing system. The term orogenic gold was defined to describe a coherent deposit group that formed in convergent plate margins. And it was defined relatively recently. We understood about plate tectonics a lot longer than that. But, sometimes the discussion between the tectonicists and the economic geologists is not very direct. But anyway, orogenic gold is thought to be directly related to convergent plate margin settings. And these comprise a group of structurally controlled deposits. They were formed in equilibrium with their crustal host rocks from low salinity water and CO2 low salinity fluids that were rich in water and CO2 at crustal depths ranging from 2 to more than 20 kilometers. And your book goes on to say that they formed in convergent margins during late transpressional deformation related to accretion or continental collision, sometimes deposited in continental back arc settings. Others interpretive originated in 4-arc settings. And so these orogenic gold deposits are aligned along faults or shear zones of crustal to lithospheric scale. So it's major fault zones. So they form over a wide range of PT conditions in marked contrast to most mineral systems discussed in this group, which formed over more limited range of depths and PT conditions. Strong structural control, we already mentioned, but the nature of that control is variable because these gold systems will form both above and below the ductile brittle transition, where rocks behave differently. Shallower than that depth, the rocks break, you have faulting, and at greater depth, rocks don't break. There are no faults. There's shear zones. So the deformation is quite different above and below the ductile brittle transition. We can talk about epizonal, mesozonal, and hypozonal orogenic gold deposits. Epizonal deposits form shallower than the brittle ductile transition. Mesozonal deposits form near the brittle ductile transition, so they may have evidence for both. And then hypozonal deposits form deeper than the brittle ductile transition, especially associated with ductile shear zones. So that's confusing, but you're getting the idea that the gold is where you find it, and that statement is true every time we look at it. So here's some examples, some sketches of epizonal, mesozonal, hypozonal deposits. So here we've got these are, a vein breccia. Here's a ladder vein. There's some stockwork that is interpreted as epizonal. And here's the mesozonal, where you got a fold hinge, some N echelon veins, banded iron formation replacement. And here's the hypozonal, which are shear zone hosted crack seal veins. So there's a very wide, these are obviously things that we could call them endogenic, right, as opposed to exogenic. So these ore deposits are forming inside the earth. And then epizonal, we can put numbers on these deposits. Less than 6 kilometers is epizonal, mesozonal 6 to 12 kilometers, and hypozonal greater than 12 kilometers. And that's the depth at which the kinds of deposits are thought to form, not where we find them. Erosion brings these closer to the surface, because we can't get below 10 kilometers, and then only with great difficulty. So I think we've sort of covered this, that epizonal ore bodies are typified by brittle structures. Mesozonal gold ore bodies, show a variety of structural styles that are partly brittle and partly ductile, and then hypozonal ore bodies only show ductile deformation fabrics. So, yeah, if you guys have any questions, don't hesitate to chime in. Oops, what'd I do? Have 2 more. All right, so here we're looking at some repetitive structural geometries of orogenic gold deposits. So here we see a combination of little offsets in the major shear zones, and maybe the gold is concentrated in those little offsets. Here we've got a big fold with some structure, some thrust faults, and the gold is concentrating in the hinges of the folds. Here we're seeing stress heterogeneities around irregularly competent bodies such as granite plutons. So, here we've got some mafic rocks being thrust over a granite, and the gold is sort of concentrated near that major structure. And then here's a very complicated diagram, a triple point or quadruple point junction of supracrustal rocks caused by inflections around competent granite plutons. So there's the structure that's paying attention to the competent rocks. And you can see the gold mineralization is concentrated in that inflection point. So it's really subtle structures that will control the gold mineralization. It's definitely a specialty science, of looking for gold. So here's the global distribution. Yes, Matt.
Go back
Yes,
one.
Yeah, sure.
Thanks. I just wanted to point out, you see the association with mafic rocks, and that's that redox control that we talked about some lectures ago. So it's very common to find gold associated with a transition to mafic volcanic rocks because of the reduced iron there.
Yeah, thanks. Good point.
Mhm.
All right, so here we've got the distribution of gold deposits. We've broken the earth down into Mesozoic and Tertiary, or Mesozoic and Cenozoic deposits there in the light colors, and then the Paleozoic in the light gray, and then Precambrian, which is differently. Now it's sort of funny because they're breaking it out three ways: Mesozoic and Tertiary, Paleozoic and Precambrian, and then the list is actually broken the Precambrian into the Archean and Proterozoic, and then separated from the Phanerozoic, which includes both the Paleozoic, Mesozoic, and Cenozoic. So it's a little confusing. But anyway, these are where the 23 largest orogenic gold deposits are. So this is, there's one in California, that's the Grass Valley mine. And then quite a few in Canada. Let's see, that must be Homestake. Huh? Yeah, that's Homestake here. And 2, 4, 5, and 9, McIntyre, Hollinger, Campbell, Red Lake, Kirkland Lake, and Dome. Are those your big gold producers, Matt?
Yeah.
Do those ring a bell?
Of yes, they all ring a bell.
So
Of
those are the big
orogenic.
ones.
Those are the big
of the
orogenic.
orogenics, yes. So we're only talking about orogenic deposits. We're not talking about the other several types of gold ore deposits. Now here are the orogenic gold deposits of China, and what you can see, China is very easily broken out into blocks that are more cratonic, in this pink, this North China block, sometimes called the North China Craton, the Tarim block, sometimes called the Tarim Craton, the Yangtze block and the Cathasia block. This is a really messed up tract of crust that's got some old elements, but it's so heavily overprinted by younger stuff that you cannot call it a craton anymore. But you can see that, the concentration of the orogenic gold deposits, are concentrated. There's obviously the Jingnan belt, that's an orogenic structure. Now this yellow is much younger stuff. That's all Phanerozoic origin. It's kind of funny because China is a very old culture, but as a tract of crust, it's one of the youngest tracts of crust on Earth. So anyway, you could have a whole course just on the orogenic gold deposits of China. Now probably the best known orogenic gold deposit is the Mother Lode of California, and everybody's heard about the 49ers and the rush to get rich and in California, and it's a very simple geology. So you've got basically an old fossil, a Mesozoic accretion, a Mesozoic convergent plate margin with the stuff that was in the trench in blue here, what's called the Franciscan Formation, and then the Four-Arc Basin, which is called the Great Valley, and then the Sierra Nevada, where Yosemite is. Those are the intrusive rocks in red, But here in the Sierra Nevada Metamorphic Belt, between the Great Valley and the batholith, you've got, this is where the mother lode is. And here you can see us zooming in. You know, these are the gold deposits along the mother lode between the Great Valley and the Sierra Nevada batholith. They're sort of here in this realm in here. Very, you can see why they call it orogenic gold. It's like, that's a really deformed belt. So it is a textbook for orogenic gold system. And here we can see it again. You know, you could teach a whole course just on that. And this is an example of mining going on in the Jamestown open pit mine. Look at all the structure in these walls, you know, of these dipping beds. You know, you can see they're dark, mostly volcanic rocks, but there's a lot of black shales in there too. I'm sure there's some geology been worked out for it. And here's the kind of mineralization you get in quartz veins associated with orogenic gold deposits. I forgot to mention the importance of quartz veins. So here you can sort of see that, you know, quartz, which is really an interesting, these quartz veins are quite interesting because what they're testifying to is there are really hot fluids that were able to dissolve silicon and then get injected in fractures and then slowly cool and crystallize out the material that was in the hot aqueous fluid to make quartz. And some of these quartz veins are rich in gold. Most of them are not. So it's like, why would some of them be rich in gold and some of them wouldn't be? And the answer is, we don't know. Yes, go ahead, Matt.
One of the conundrums in ore deposit geology is that, so people interpret the conditions, the fluid conditions, by looking at things like fluid inclusions in the quartz veins, and then assume that those temperature, pressure, salinity conditions applied to the gold mineralization. But actually, it's very hard to establish a chronology of when the gold was actually precipitated relative to the quartz. So not everybody agrees they're coeval. Some argue the gold's later. So
arguments at every level about this stuff.
Yeah, absolutely.
But it is true that if you're in a metamorphic belt with a lot of quartz veins, it doesn't hurt to look for gold. And it would be orogenic gold if you found it. So, we got a video here. These kinds of golds are just fun. So let's watch it.
This insane gold specimen, known as the Dragon, was found back in 1998 at the Colorado Quartz Mine in California, and it's still considered one of the most iconic gold pieces ever discovered. The detail is wild, bright, sharp crystals forming what looks like a body, legs, and even a rising plume, pure California gold character. But here's where it gets mind-blowing. Gold like this didn't start on Earth. In 2017, scientists actually witnessed two neutron stars colliding, creating a massive explosion that made a ton of heavy elements, including a whole lot of gold. That ancient stardust eventually ended up here, forming treasures like this. So yeah, it's not just beautiful, it's cosmic.
Yeah. Yeah, there's some good videos out there about gold. What happened to my little arrow? Why can't I find it?
This insane gold.
There we go. All right, so this is a situation for California in the Jurassic and Cretaceous when these gold deposits form. So we've got, this is the Farallon plate being subducted beneath what's going to become California. There's the accretionary prism, which is now the Franciscan complex. If you go to San Francisco, you're walking on the Franciscan. Then there's a Four-Arc Basin, which is now the Great Valley, and represents a huge agricultural region. And then the magmatic arc associated with the subduction, that's the Sierra Nevada batholith. and the gold mineralization is happening here. Okay. Now this scenario is going to be, we're going to revisit it when we get to the Carlin deposit. So the Carlin, that gold is going to form way back here to the right side of this diagram, but it's going to be partly reflecting what happened with the subduction of the Farallon plate. So they're not unrelated. They're not as clearly related. The Carlin and this subduction zone is not as clearly related as the orogenic gold of the mother lode and this subduction relationship. Now, the timing of the mineralization in the mother lode has always been something people wondered about, and this shows you the age of, this is basically beginning in the late Jurassic. So there's the Cretaceous Jurassic boundary there. And then this is this is about the end of the early Cretaceous. So the late Cretaceous is over here. So this is showing you the sort of the volume of magma associated with that magmatic arc. And you can see that it was modest, and then it decreased a lot, and then it really rose a lot towards the end of this episode. Most of the Sierra Nevada batholith was created after the gold mineralization. And so this is showing you for both the Klamath Mountains. I didn't show you where that was very well. Klamath Mountains are up here, so they're kind of a continuation of the mother lode. So there's the Klamath Mountains and Sierra Nevada foothills, or the mother lode, right? And let's see, the asterisks are the mineralization ages determined for the Klamath Mountains, which are all in this mostly late Jurassic and earliest Cretaceous episode. And these blue dots are 4039 mineralization ages. Remember, we talked about that technique for getting ages. And there's also a uranium lead age in there. And you can see that this is for the Sierra Nevada foothills. And the oldest one is about the same age as the Klamath Mountains. But there's a lot that are a lot younger. Most of the mother lode is younger than that Klamath gold, which is kind of interesting. And then these are potassium argon and rubidium strontium mineralization ages for the Sierra Nevada foothills. And you can see that those range in age. And then there's a potassium argon age for the Klamath Mountains that sort of is about that of the mineralization ages. So there's some interesting variability just between the Klamath Mountains and the Sierra Nevada orogenic gold that we don't understand. All right, so orogenic gold is deposited from low salinity, which, on the order of 7 weight percent or less sodium chloride, and fluids that are rich in water and CO2, typically 5 to 20% mole CO2, and they can also have some methane or nitrogen, a little bit of sulfur, weakly acidic pH of 5.5 or so. So, Matt, you were mentioning that's probably based on fluid inclusions, but that maybe that's not the fluid that caused the gold mineralization. Is that correct?
Oh, that's what people argue. Yeah, they argue about the nature of the ore forming fluid itself. But yes, that would be mostly based on fluid inclusions.
Yeah. So there's several mechanisms by which the gold is deposited from such fluids. There's fluid wall rock interactions. There's the sulfidation of iron-rich wall rocks. There's fluid exchange with reduced carbonaceous shales, and there's phase separation. We'll talk more about phase separation. That's where the fluid separates as immiscible liquids. We talked about that, into mostly a low salinity phase and a high salinity phase, and that this may have accompanied hydraulic fracturing caused by overpressured fluids. This gets really complicated fast, doesn't it? So this is a way that your book shows the metamorphism or defolatilization, which is the loss of fluids from crustal rocks. So as you heat up crustal rocks, they start to dehydrate, and it's thought that those crustal fluids are what transports the gold. And your book says this is the only viable genetic models for orogenic gold systems. So that's a bold claim. Do you agree with it, Matt?
I agree, it's a bold claim.
but it may not.
Because people still argue all the time about orogenic gold deposits. So yeah.
But there's a significant fraction of people that would subscribe to that statement, even though not everybody does.
Mm-hmm. Yeah.
Yeah. So the thought is that the fluids that are responsible for mineralizing gold mineralization in these orogenic gold is that the fluids are coming out of metamorphosed lower crust rocks, especially under amphibolite facies metamorphic conditions. But just like we're starting to think about Thanksgiving turkey. When you cook a turkey, the key thing is don't dry it out, right? And what that means, you left it in there too long, in the oven too long, which the heat drove off the fluids from the turkey. Now, cooking rocks is not the same as cooking a turkey, but the principle applies. The longer you heat something, the more you heat it, the more it's going to give up the water, and that fluid is going to move, and it's going to carry stuff with it. And in some cases, it'll carry gold, and it will rise, following the mineralization system into it will be transported to a place where it can be where it will crystallize. So these are just a number of ways that can happen. How you can get the fluids. Yeah, jump in.
Well, so if you notice in each one of those models, there's granites. So there are people who still argue for magmatic, at least contribution to orogenic gold deposits. Right? In other words, they're not just providing the heat to devolatilize crustal rocks, but maybe providing metals, gases, and things like that directly.
Yeah. And this is going to get real pertinent real fast, because we're going to talk about a relatively new class of gold deposits called intrusion-related gold, right? So here, even though they show the plutons somehow associated, it's not clear what the relationship between them, the intrusions and the gold mineralization is. With the intrusion-related gold deposits, the model is tying the mineralization much more closely to the intrusion. And it may be that these are end members of a system that is overall similar. But all right, so here we've got an orogenic gold mineralization model with two end members where there is no underlying or adjacent older mantle lithosphere. Devolatilization of subducted oceanic crust and sediments are required. So this is attractive. The fluids are coming off the subducted material. We can see how that might apply immediately to the mother lode of California orogenic gold, and those fluids are responsible for the transport of the gold. And so in B and C, it's less clear where the relationship between the subduction and the mineralization is. So here you're seeing a situation where there's subduction zones, but the zone of mineralization is way separated from it. So the transport, is more complicated. And the other thing is you could have an episode of subduction that mineralized the mantle lithosphere, but that sort of preparation of the lithosphere was hundreds of millions or even billions of years before the actual mineralization event, but that without that pre-concentrated lithospheric mantle, that the ultimate mineralization would not have been possible. Right here, these things are happening in real time. Here, this might be a significant time lag between the fluids coming from the subducted slab versus the involvement in the mineralizing system. Any questions about that?
Well, we do have good seismic evidence of lithospheric structures going down through the crust into the lithosphere. So there are ways of getting metal-rich fluids from those depths.
Yeah.
So
I guess the point is that the sequence of events, it doesn't have to necessarily be bang, bang, bang. It could be, the first step is accomplished a long time before the last step.
exactly.
All right, this is the temporal distribution of orogenic gold systems. And we're showing some of the major deposits in here. These are the names of there's the mother lode. There's some Chinese ones. Homestake is in South Dakota. Here we got some in Canada. I think Timmins is the one in Canada. Do you see any?
That's a big mining gold camp.
Yeah, in the Shield.
Yep.
Yeah. Now you'll see over and over again, they just keep bringing in these supercontinents as somehow explaining something, which I don't think it does, because if you pull away those gray bars, what you'll see is that you've got a long time in Earth history when there's no gold, no major orogenic gold in the boring billion. We'll talk more about that. But you can see that at a glance, if you're looking for gold, you want to be looking for the most part, you want to be looking for Phanerozoic terrains or in the Archean, because that's where the gold is known today. So, yes, John. Go ahead.
Yeah, so jumping back, I mean, you really don't think this dispels your theory that there was no tectonics back in the boring billion, that those couple Olowith or whatever assembly have something to do with something else.
Yes. So, yeah, we can get into this. Next lecture, we'll be talking more specifically about it, but it is useful to start thinking about the temporal distribution of deposits. But you can see what they're doing is, this is, what's the difference between a supercontinent that lasts for a billion years, with the exception of this little white thing, which is kind of weird, and a single lid planet where there's no plate tectonics. It's basically the same thing. If this is a single supercontinent that lasted that long, then that's the same as saying there doesn't seem to be much plate tectonics. And I do want to you said there wasn't any tectonics. That's not quite right. So it was a different kind of tectonics. So tectonics is something that any actively convecting body, silicate body, is going to have. Venus has tectonics, but it doesn't have plate tectonics. And that's actually where the idea of the single lid tectonics came from, was studying that. So no, this, in fact, one of the reasons I got interested in mineral deposits was because I was looking for independent arguments for Earth's tectonic history. And there is very much a signal in ore deposits. And we'll talk about why that is in the next lecture. But so notice the absence of orogenic gold deposits from the Mesoproterozoic. Why is that? And The book says this, and yet they sort of ignore that they said it. The missing ingredient is direct evidence for subduction-related processes such as the formation of porphyry, copper, gold, and VMS systems, and critical marine volcanic sedimentary assemblages that relate specific to subduction. So they're kind of saying, you know, the problem is we're not sure that plate tectonics happen, but then they go and show these supercontinent cycles. So I just thought I'd point that out because you'll be hearing more about their supercontinent cycles later. You know, normal granitic rocks for some reason. I keep jumping around here. And IRGSs are characterized by widespread arrays of sheeted auriferous quartz veins in the brittle carapace at the top of small plutons, where they form high tonnage but low grade gold deposits. So here's Fort Knox, Alaska is the type locality. So I guess that's a pretty well named pluton, which I imagine was named after they found gold. So here we're looking at a cross section from south to north, not to scale. So we're assuming this is a few hundred meters or a few kilometers. And what we see is there's a country rock schist, you know, and then we've got a coarse grained granite down here, and then a medium grained granite here, and then a fine grained granite, and then a bunch of small shear zones, and their coloring scheme doesn't really help us much, but either the purple, I think the purple are the mineralized quartz feldspar veins, and these other things are pegmatites and apatite. And it's complicated intrusion. There's 3 different granite phases, which we can see. And the gold mineralization is hosted by these sheeted quartz feldspar vein arrays and late stage shear zones. So let's see if we can figure out. This is the Alaska Yukon Tintina gold province, sort of between the Farewell Denali Fault and the Caltag Tintina Fault up there going through Yukon and into BC. And this is one. I think this is the one we were just talking about, the Fort Knox. This is another view of it. Here we're looking at the epizonal, the mesozonal, and the hypozonal. This cross section is obviously not for this pluton. This is just sort of conceptual. And then they're putting in here the different deposits that where they would put them. So for example, Fort Knox is thought to be a hypozonal, you know, IRGS. And here's another one in Alaska that's a little bit more mesozonal. And then these are epizonal. So interesting range of conditions under which gold can, in these IRGSs, deposits can form. So the sources of IRGSs are thought to be volatile rich magmas with low oxidation states generated by partial melting of metasomatized mantle lithosphere, fertilized during prior subduction to form volatile rich mafic melts that ponded below the moho. That's the stage 1, so it comes up from the mantle. This is the lithosphere, and then this is going to be the crust up here. Very conceptual diagram. And this caused crustal melting with metal and volatile transfer across chemical gradients between the 2 types. That's what we're seeing here in stage 2, leading to gold deposition in near vertical extension veins or arrays, scarns through the fluids we're seeing here. So this is the scheelite dome IRGS. I'm not sure where that is. Have you ever heard of it, Matt?
Sorry, say that again?
Have you ever heard of the Scheelite Dome intrusive complex?
No, I haven't. But
Yeah.
I do want to point out the problem with the figure. So it says uh, to form volatile rich mafic melts that ponded below the moho, but actually they've got that ponding in the lower crust
Oh, you're right.
with a
They do.
certain.
Yeah, I
Yeah.
didn't see it over here. Good spotting. Keep me awake. All right. The consistent association of IRGSs with certain magma types, their consistent polymetallic metal associations, gold, bismuth, tungsten, arsenic, molybdenum, tellurium, and or antimony, metal zonation patterns, and the presence of gold in the high temperature melt inclusion strongly suggest a magmatic hydrothermal origin for these deposits. And so they have several characteristics, including these associations with intermediate to felsic intrusions that are relatively low oxygen fugacity, that can be related to potassium-rich basaltic parent magmas coming out of the mantle lithosphere. Their hydrothermal fluids are carbonic, that is CO2 rich, low salinity, and they're associated with these, other ore assemblages, low sulfides, less than 5%, weak hydrothermal alteration zones, and that magmatic signature mentioned in 1, that's consistent with 6. They have continental within plate tectonic settings, and they apparently form near cratonic margins. So good targets are orogenic belts that host evolved felsic intrusions with low oxidation states, but overall I-type chemical characteristics. Remember, we talked about the 3 main types of granitic magmas, and I-type being the igneous type is associated with subduction. Chemical and petrographic characterization of the intrusions is a key guide to prospectivity and area selection on the province scale. These are typically magnetite poor granites or Monza granites that are weakly metaluminous to weakly paraluminous. That's a little bit of detail. All right. So now, any questions about IRGSs? That's, it's sort of a new category. The relationship with the orogenic gold is maybe, there may be some relationship. We're not really quite sure, but any questions, just chime in. Now we get into the Carlins. So the Carlins, this is a big deal, and it's a pretty recent deal. So the Carlin Trend is one of the largest gold provinces in the world, and has made the United States the world's 3rd ranking gold producer, which is almost entirely from production in Nevada in the Carlin. So these occur in a very complex geologic setting in north central Nevada. And this region is generally thought to mark approximate position of the boundary between the old Proterozoic and older crust to the east and the material that was added in Phanerozoic time to the west. So you can see all these mines. There's the original Carlin Trend. There's Elko, which is definitely, if you want to go to a gold rush town today, that's where you'd go. Stop in Elko and see what the chat is at the local coffee shop. Now, these are some. Go ahead.
I was just going to say, Elko is a lovely little town. It's got all the places you want to eat as long as you have a choice of 3.
When was the last time you were there?
I was there in 2013, 14, something in there.
Yeah, it might have changed, but there might be 4 or 5 places they can eat now. But I looked it up, it's only about 20,000 people.
Yeah, they're all miners.
So the Carlins are called the invisible gold deposits. So that's like, what? How can you find something you can't see? It's like, well, okay, pay attention. But here's Nevada, right? And so here's the craton. There's there's our Canada's, the Superior Craton. And as you get close to the Pacific, the craton gets messed up and it gets tectonized and gets deformed and it gets intruded by subduction related igneous rocks. They're related to the formation of this, this accretionary belt that formed in Phanerozoic time. And you can see it's kind of near that margin, but the way we're drawn that margin between the deformed older crust and the new crust, it's not quite aligned with that. So it's like everything else with gold. It's not as simple as it's like, please just make it simple. Sorry. All right. So this is kind of an interesting map. This is Nevada, most of it. Las Vegas down here, where most of the people live, is not shown. But there's the Sierra Nevada. We were talking about that. As it related to the mother lode and the orogenic gold. And here are the deposits and the known ages, right? So these are significantly younger than the ones of the mother lode. The mother lode was like 100 to 170 million years. These are all in the 30s and the 40s. So you can see that they're a little bit older in the north and a little bit younger in the south. So the oldest one is what, 40, something around, 40s, 41-ish, 42-ish millions of years old. And as you go south, it goes to like 32. So this is being shown as the initiation of Cenozoic magmatism in this region. And it did a funny thing. It started earlier in the north than it is the south, and way down here it's at 12 million years. But the gold deposits are limited to this, the first, what is that, like 8 million years in this southward migration. Now, the other thing you notice on here is the distribution of calderas. And the calderas are interesting because they have their own mineralization. So McDermott caldera is somewhere up there, and it's of interest to people for lithium mineralization. So Nevada definitely is, it's mining, its evolution as a mining state is not over yet. So there is this interesting age progression in the deposits that's associated with the age of the beginning of igneous activity in the region. So Carlin type gold deposits are epigenetic, right? They formed near the surface and they formed in the Eocene about 40 million years ago. And here we see a mine, huge. Those are little trucks. Well, they're not little trucks when you get up close to them. They're big trucks, and you can see the size of this mine. And that's kind of the stuff that they're mining. So this is basically a silicified, decalcified siltstone mudstone of early Ordovician age. So this was originally some kind of a passive margin sediment on the margin of North America, and it's been through the ringer since then. So that the ore grade here is about 0.2 to 0.25 ounces of gold per ton. So just for you to understand what that is in ppm, which we talk about a lot, 28.3 grams per ounce is, so 0.2 ounces per ton is 5.7 grams per ton, which is 5.7 parts per million. So that is not much, but the price of gold and the economics of these deposits is such that it's worth it. You can see from that mine that they wouldn't be doing that unless somebody was making a good amount of money. All right, so these are associated with arsenopyrite. So everybody knows what pyrite is. You know, pyrite's just FeS2. And arsenopyrite is arsenic replacing one of the sulfurs. So FeASS, FeS. So FeS. Name for my next band. Contains gold. So this is sort of that's 500 microns. So that's half a millimeter scale bar. So this is about a millimeter apart across. And so these are that looks like reflected light. This looks like a scanning electron microscope image, and all of the different things. That's PY is pyrite. Here you see this Arsenian pyrite, right? And that's where the gold is. All right, so this is how Muller et al. Depict the Carlin deposits. So here we've got pretty complicated geology, and it isn't simplified by the fact that this Jurassic diorite doesn't seem to go anywhere at depth, which doesn't make sense because the thrust fault is here. But this is an early Paleozoic thrust fault involved in one of the orogenic. There's the Ordovician siltstones that we were talking about, Jurassic diorite, but that can't have been responsible for mineralization because the mineralization is much later than that. Then Devonian siltstones, right? Those get, and then Devonian carbonates. And then these are sort of the zones of mineralization, Carlin type mineralization. They're just sort of in these Paleozoic sediments. So this is the system that Muntian and Klein have written up. So here we've got the brittle ductile transition in the crust, and the lower crust is devolatilizing. You've got these metamorphic fluids coming off, and then they're also calling on groundwater to come in and mix with these metamorphic fluids, and somehow that is responsible for the mineralization, right? So here, the interesting thing is they're linking three types of these deposits. There's the Carlin type, right? You're showing a structure that's controlling the Carlin mineralization in these lower early Paleozoic carbonates, and then they're showing epithermal deposits with a lot of the same processes going on, just shallower. And then they've got some kind of a relationship with an igneous body that is linking it to a porphyry deposit, as well as something coming off of it. So this almost looks like an orogenic or, oh, hello, Clint. You got a question?
No, I just wanted to point out this reminds me of those antacid commercials with cross sections of the stomach.
Yeah. Well, the point is, it's like, you know, we've got all these different kinds of mineralizing gold mineralization systems, and it's like, is it really that complicated, or or have we not figured out the relationships? And you know, we've already explored the relationship between the orogenic gold and the IRGSs, and then we're like, okay, well, what about the Carlin? And so anyway, so you know, as you know, a lot of us, we like to pigeonhole deposits by type, but nature is much more of a continuum, and if we can link them in a continuum, then we have a better chance of understanding, you know, what's really going on. So CTDs, Carlin type deposit, that's what a CTD is. And so there's lots of CTDs, but some of these may be transitional to shallower epithermal deposits and deeper porphyry deposits. That's the bottom line of that. Yes, Clint. Yes, Clint.
Another diagram question would be right there under Carlin type deposits, there's a symbol that's commonly used for thrust faults. What does it mean in this case?
Well, it means there's a structural control. That there
Okay.
is always a nearby structure, and the big structure in that part of Nevada is called the Robert Mountain Thrust, which
Mm-hmm.
is a late Paleozoic. I think it's related to the antler orogeny, which was sort of at the end of the Paleozoic, a little bit before our own Ouachita orogeny, but the there is this perception that somehow this Paleozoic structure is affecting the Eocene mineralizing system because they seem to be found together. But you don't really get much more detail than, you know, a wispy line with teeth on it like that.
It'll work, but it's yeah, it makes his own weakness and all kinds of stuff.
Yeah, I imagine if we were at the University of Nevada, Reno, which is sort of the epicenter of academic research onto these things, there was probably be a whole course on Carlin type ore deposits. All right, so this is the Cortez Hill deposit. Let me go back. Yes, John.
I apologize. On the slide two before this, I saw it's trapped in siltstones. Is it the Devonian or the Ordovician?
Well, I mean, Cambrian, Silurian, Ordovician, Devonian. I mean, the Devonian is slightly younger than the Ordovician. So there's the Ordovician being thrust onto the Devonian. Is that
that
answer
where
your
it's,
question?
is it at, well, yeah, I mean, I'm just wondering, is it on the shallowest, youngest formation then, or
Well,
the shallowest formation?
the thrust faults, the whole idea of thrust faults is these bring older rocks on top of
Yeah,
younger
no,
rocks.
I apologize about that, but it's in the shallowest formation.
Yes, yes, it's close to epithermal, right? The Carlin types are so interesting and unusual. We've broken them out by themselves, but to a first order, they're kind of epithermal. Would you agree with that, Matt?
Yeah,
Yeah,
fairly
so
shallow.
yeah.
Have we found Carlin type anywhere else in the world?
Yes.
Ooh, where have we found them, Matt?
Oh, I couldn't tell you all the places, but there's some in the Yukon, for example. So yeah, they're around and around,
Yeah.
or
Yeah.
they are around. Sorry.
All right. So we talked about Cortez Hill deposit. Let's go back and see where that is. Because Cortez Hills, it should be in here somewhere. Why don't I see it? It's somewhere at one of these.
Right in the middle, 35.7.
Ah, yes. Thank you. Thank you. So you can imagine that the companies are very interested to work out the detailed structure. And here we're looking at, these are, I'm sure these are drill cores, right? Because this is subsurface. That's a lot of alluvium on top, right? So you've got to get down into here. And you want to understand what is because you want to plan the pit. If you don't understand where the gold is, then you just put your pit in. It's like, oops, wrong place. We should have done somewhere else. So they'll do a lot of drilling like this. And this is a really good example. So here we're looking at the Cambrian, Ordovician, Silurian, Devonian, right? And then over here, we've got some Jurassic intrusions. There's a granodiorite. Where's the rhyolite? Yeah, I don't know. And then
The rhyolites, the sort of stringy things, right? So the Cortez rhyolites are those really thin, stringy, look like veins.
the gray.
Yeah.
No, those are the Cortez rhyolites. Okay, yeah, I see.
Yeah.
Yeah. So these
Oh,
are
you were talking
all.
about the okay. Yeah.
Yeah, I was
sorry.
wondering about
It's
the
JR.
Jurassic rhyolites.
Yeah.
Yeah, but the Cortez rhyolites, that's really good to point out that these are clearly, permeating this section. And I'm guessing those, you can see all the ages here, that these Cortez rhyolites are basically the same age, 35.67 or so. And then look what the gold mineralization is, right? It's definitely paying attention to something. Here's a structure that it's related to. And then the intrusion is also related, sort of sensitive to that structure. So you can see why they would go like, okay, we want to build the pit. I mean, depending on how rich these ore bodies are, they're going to want to build the pit over here, right? And that's 1 kilometer. You don't want to dig your pit over here because they just didn't find anything, you know? So it's like, okay, I think we're starting to dig here. So, kind of cool. That's the level of detail. Can you imagine how much work that is? All right, so here are 32 active CTD mine locations in Nevada. So, you know, they're in blue, those are the Carlin types. And then in the white, this is the distal disseminated silver gold deposits. Don't know what that means. Epithermal deposits over here. Pluton-related deposit. Is that an IRGS? They don't call them that. Lone Tree
I
and
think they're
Merrick.
more, I think they're more porphyry-like. Gold porphyries
Okay.
would be my guess. Although when you go from a gold porphyry to an IRGS is probably a continuum as well.
Yeah. I mean, a lot of these names are local. Like that's just what somebody started calling them. And so everybody calls them that. And then different part of the world, they're the same thing is called something else. We set up committees to classify things, but I think that would be a committee I wouldn't want to serve on. But, you know, now that's 32 active CTD mine locations. That's not mines. Because the problem is how do you count the mines? So here is the Pinson mine. It's a small inactive Carlin type deposit. It's got 5 different pits, right? 1, 2, 3, 4, 5. Do you count that as 1 mine or 6? So anyway, that's kind of the very specific sorts of targets that this community is working on. Okay, so here we've got that same diagram we showed before, you know, the gold production in the United States and in the light orange and in Nevada in the dark orange. And you can see that, you know, Nevada was never an important gold producing state until, you know, it took off in 1985 or so, or 1990, and it just doubled and doubled and doubled again. So this is going up to, looks like 2025. It looks like Carlin production is decreasing, but one has to imagine that with the doubling of gold prices, some things that were uneconomic in the past are very economic now. So interesting times in Nevada. Now, what's going on? We sort of understand where they are, but what the hell is going on? So this is a really interesting geology story. So this is the Nevada Plano, which is it's basically taken the from the Altiplano of South America. This is an orogenic plateau, an elevated region, and this will come back when we start talking about the placer gold in California. So what we've got here is an elevated region that formed because the subduction beneath California as we went into the early Cenozoic, we were subducting younger and younger oceanic lithosphere, and young oceanic lithosphere is buoyant and resists subduction. That's part of what's going on to make the altiplano of Peru. So you're basically compressing the region, and it's growing, and that keeps happening as long as you keep subducting younger and younger oceanic lithosphere, and that's what's happening here. So you built this thing up. You had, you know, you had this high region here. This was probably the Continental Divide. We know that because we can see in some of the sediments along the Gulf of Mexico that the zircons are coming from Jurassic and Cretaceous plutonic rocks, which are only found in this region and farther west. So we've got lots of evidence that this elevated relief actually formed at this time. So what happened next was we're subducting younger and younger oceanic lithosphere of the Farallon Plate. And this is the west coast of the United States. Here you can see Baja California, Los Angeles, San Francisco, and this is going to be up near Oregon and Washington. And so this spreading ridge associated with the boundary between the Farallon Plate and the Pacific Plate gets subducted, and that changes everything because you're no longer subducting very young oceanic lithosphere. You've actually transformed the margin into a strike-slip fault. And this was work that got one of my geologic heroes, Tanya Atwater, famous as a graduate student in the early 1970s because she worked this out from studying magnetic anomalies on the Pacific seafloor. You know, and this forms the San Andreas Fault, a very famous strike-slip fault, and that ultimately tore Baja California away from mainland Mexico. You know, and this is the situation we have today. So we go from a time when there was very strong compression of the overriding plate, the North American plate near the trench, to a time when that compression was released because of the formation of the strike-slip fault. So once that ridge was subducted, you see a relaxation of that Nevada plano. It's a cool story. So that happened. Beginning about 17 million years ago, this region was no longer elevated into the Nevada plano. It collapsed and became basically what we see today, the basin and range. So, you know, we argue about how much extension happened between the Colorado Plateau and the Rocky Mountains and the Sierra Nevada, but, you know, for the most part, it was this region was doubled in its width. And so that everything sort of relaxes, and that leads to a bunch of melting in the underlying mantle and sort of sets in motion lots of things, like all kinds of rhyolitic eruptions in here. But also, you know, so you can see this age, 17 million years and younger, is when this collapsed into the basin range that we see today. So the time of Carlin mineralization is related to this time, right? So this is the orogenic plateau. The Carlin trend is sort of up here like this, but it was the Carlin mineralization is happening during this time when the Nevada plano was at its peak, which is an interesting clue. So this was a situation when the Carlin type deposits were forming, and then after that, we have all of this extension and erosion, and we see that the deposits exhumed today. All right, so the amount of elevation on the Nevada plano varies, but in general, what we see is something like this. Here we have the Farallon Plate being subducted. There's the Franciscan Formation. There's the Great Valley. There's the Sierra Nevada batholith associated with the subduction. And then back here, we get the Nevada plano with this shortening, and you have this relief. There's the Continental Divide, you know, drainage this way to the west and from this way to the east. So here we've got it reconstructed. People are drawing it like that based on a number of proxies. Now, okay, we've talked about the Nevada plano. Here we're seeing, so really interesting, we see the outline of Nevada, And we see this is the Paleo divide that existed in the early Cenozoic and the Eocene. Rivers flowing to the west, rivers flowing to the east. And, the Carlin type deposits are up here. And then there are old river channels that in California that we'll be talking about when we talk about the placers and the paleoplacers that are flowing to the west. And these were pretty big rivers. So we know that something like this existed because you can stand on the old river channels. And we're going to talk more about these placer gold deposits in later in this lecture. So these are the characteristics of the Carlin type gold deposits in Nevada. So formed from 42 to 34 million years ago. I don't think that was when compression changed to extension. That was a little bit later, but there was plenty of igneous activity in this region. Occurs in clusters along old reactivated basement rift structures, preferably in carbonate-bearing rocks. We hear about carbonates being really good, places for gold for different kinds of mineralization because they're so reactive. All kinds of alteration of those rocks, and these fluids are thought to be were not so hot, but again low salinity but CO2 bearing, and mostly formed at depths less than about 3 kilometers. So here's kind of a section of what we're thinking is happening at depth. Here's the Laurentian Craton. It's not really Archean, but it's older crust over here, and to the west, it's more accreted material, and the Roberts Mountain thrust brings this section up over it. And sort of this is sort of the area of Carlin type mineralization. So there are jobs in Nevada Gold, both jobs and internships. That if any of you are interested to explore that, Geologic Society of Nevada posts these, and they send out email announcements. So if you become a member, you get on the email list. Students are more than welcome to join Geologic Society of Nevada for $25 for the year, and they will get all of the job announcements. Anyway, now this switches over to 8.5 in the book, which are gold-rich submarine porphyry epithermal VMS systems, which are hydrothermal. And I think we moved this into the seafloor stuff. Yeah, we should. If we haven't, I'm going to skip that over. And we'll move that into submarine deposits. Matt, is that okay with you?
Yep, that's fine.
Okay. I'll just, you can pull that out, and I'll just jump into 8.6, which are the high sulfidation epithermal gold systems, which are clearly hydrothermal. So here we've got one, we've got a felsic intrusion, some hydrothermal brecciation, different kinds of alteration of the surrounding rocks. So this one is showing the argillic. We haven't talked much about alteration halos. You can dig into that if you want to at some point, but you can see it's not very deep. There's the water, it's below the water table, so you've got this heating and setting up of hydrothermal activity that's going on, but clearly epithermal. So these are major fossil hydrothermal systems, and they generally just form right below volcanoes, and they're generally subdivided into two main subtypes: high sulfidation and low sulfidation. And this is a very important distinction in this understanding ore deposits: high sulfidation and low sulfidation. Like, what is that? So sections 8.6 and 8.7 focus on high and low sulfidation epithermal gold deposits. So let's figure out what sulfidation is first. So, these high and low sulfidation always refers to epithermal deposits. That's true, Matt, isn't it? We're not,
Yeah.
we don't talk
Yeah,
about. Go ahead.
No, you don't talk about high sulfidation PMS or something like that. No.
So they form from,
But,
what's that?
yeah. And actually, now that I say that, I have seen some people refer to some VMS as high sulfidation, but it's mostly applied to epithermal deposits. Let's put it that way.
So it's basically the importance of a sulfur in the mineralizing system, as I understand it. So the high sulfidation deposits, if you have a lot of sulfur mixed with water, you're going to have sulfuric acid. You'll get these acidic fluids, sulfur-rich fluids that come from deeper magmatic, that should be magmatic, not magnetic, leading to intense alteration. And you get, these deposits contain sulfide minerals and are associated with advanced argillic or clay forming alteration. In contrast, low sulfidation deposits develop from neutral to mildly acidic fluids that mix with meteoric water, resulting in less intense alteration. They're typically found closer to the surface than high sulfidation and generally lack sulfide minerals. Does that cover it, Matt?
Pretty much, although low sulfidation ones can have lots of sulfur, it's just not sulfide. So you get in low sulfidation deposits, you can get a lot of sulfate minerals like alunite, jarosite, things like that.
So unless it's sulfide, that's
Yeah, so
the key,
it's
the amount of
it's
sulfide.
kind of yes, not the amount of, it's the acidity, the alteration style, and how reduced the sulfur is. Yeah.
Okay, thanks. So here we've got a geothermal system. There's a volcano, a little crater lake, so that gives us some water coming in. And here we've got meteoric water. There may be some water coming out of the crystallizing fluids. There's an intrusion with like dikes and fluids coming off of it. And here we see the high sulfidation is associated with the magmatic center, because it's being dominated by, the perhaps a contribution from magmatic fluids. And the low sulfidation is off to the side where it's very difficult for these fluids to get involved. Does that capture the sort of the mineralizing system the way you see it, Matt?
Yeah, pretty much. I mean, you can see the temperature ranges there. So the high sulfidation look like they're higher temperature systems. And as you said, much more magmatic influence than the low sulfidation.
Yeah, thanks. All right, so that, talking about low sulfidation epithermal deposit takes us to high sulfidation epithermal gold systems. And, you might be going like I was, like, wait a minute, why couldn't we put Carlin in one of these? And Matt, do you know why we don't typically associate Carlin with a high sulfidation epithermal or low sulfidation epithermal?
I guess because they're a little deeper.
It's the depth, you think that's,
I think so, yeah.
Yeah, so okay, so interesting. All right, so, and then there's also, some people will add an intermediate sulfidation type, but we won't worry about that. But the high sulfidation systems, they typically sit above tip abyssal intrusions, sometimes grade downwards into porphyry copper deposits, which makes sense, right? We've seen the role of these fluids, both magmatic and meteoric waters, playing an important role in porphyry coppers. So we can imagine that some of these high sulfidation deposits in particular are just shallower expressions of those same processes, right? Mineralization usually extends from shallow intrusions into the country rock consists of veins and associated breccias and buggy textures and pervasive silicification. You know, you get the idea that maybe you could, you know, somehow relate porphyry systems with the intrusion-related gold systems, you know, sort of at depth, and then high sulfidation, epithermal associated above that, and low sulfidation off to the side. And you sort of feel like, oh, you could sort of put these things together in a more systematic way that makes it slightly less confusing. This guy's good.
In traditional models, like these great ones from Greg Corbett, high sulfidation and low sulfidation systems are usually put into completely separate environments. But it's important to note that there are exceptions. That hill over there is a high sulfidation epithermal system. The big ridge is made of massive and vuggy silica, and it has all the other characteristics that you normally expect in a high sulfidation system. And this vein here has all the textures that you normally associate with low sulfidation systems, just 500 meters away. This piece here is mostly saccharoidal textured quartz, in between some beautifully preserved bladed carbonate replacement texture. That combination indicates somewhere in the upper parts of the boiling zone in a low sulfidation epithermal system. And here, from a few hundred meters along the same structure, is a piece of crustiform banded quartz, typical of the kind of texture you see in mineralized low sulfidation epithermal veins. So now I'm about 3 kilometers away on another high sulfidation system. Those low hills behind me there are a big lithocap of silica alunite alteration. And out here on the flats, just a few hundred meters away, is another beautiful low sulfidation epithermal vein. It's got absolutely beautiful crustiform, coliform banded textures, exactly what you find in typical low sulfidation vein systems. Now there's a little bit of question about the relative timing of this vein versus the high sulfidation alteration back there, but the coincidence of position just can't be ignored. So if you're working in a high sulfidation epithermal system, don't ignore the possibility that there could be low sulfidation systems with equally good or sometimes better mineralization out on the shoulders of where you're looking. This is another video in the series of Fieldcraft for geologists. This is the edited highlights version for YouTube. If you'd like to see the full video, go to the link in the description below, and for less than the price of a short course on epithermal systems, you'll get the full version of this video, all the other videos in the Fieldcraft series, and anything else I shoot as I find interesting things in the field.
All right. Alteration in gangue assemblages are often used to distinguish high and low sulfidation deposit. He kind of alluded to that, but low sulfidation systems tend to be dominated by quartz plus adularia plus cerussite. So adularia is a low temperature potassium feldspar. There we can see a nice photograph of it. And cerussite is a name we give to very fine ragged grains and aggregates of white mica, typically made up of muscovite or illite or paragonite. And in contrast, high sulfidation systems, their alteration is dominated by quartz, alunite, or acid sulfite. So alunite is a calcium aluminum sulfate hydroxylated. So, you know, that is one of the keys to distinguishing between the two epithermal sulfidation types. So 1/3 of the 12 largest producing gold deposits in the world today are high sulfidation deposits. And they also produce significant byproducts, such as indium. So here we've got a high sulfidation gold ore with vuggy silica textures from Indonesia. So what happens here to get this is the ground mass. This is a a porphyritic volcanic rock where there were originally plagioclase phenocrysts, and they were replaced by clay that eventually completely leached out. And the rest of this is mostly silica as a result of the alteration. So, yes, Clint.
Yeah, I'm interested in how the clay gets leached out. I mean, it's clay, so apparently there's enough porosity and percolating fluids to actually physically move the clay out.
I guess. I mean, that's a good question, and I wish I had a better answer. Maybe Matt does.
Sorry, say that again, Clint.
But
So
we were talking about how the clay gets removed from this rock, to make the vuggy texture.
I mean, I suppose fracturing of the rock helps, and volcanic rocks tend to be pretty fractured up anyway. So long as the clay could get to a bigger crack.
Well, you've got porosity and permeability. So you can see there's a lot of porosity here. And that's because the clay minerals, presumably what happened is you altered the feldspar to clays, and the clays get removed by further acidic reaction, would be my guess.
Another PhD for you, Clint.
Indeed.
Okay. In most high sulfidation epithermal gold and I guess silver deposits, two hydrothermal stages can be distinguished. There's an early intense acid leaching of the wall rock by the magmatic vapor that condensed into the groundwater, cooled to less than 300, and was acidified. Isn't hard to do. H2SO4 comes with the reaction of sulfur dioxide in groundwater. It's by that reaction. It's called the disproportionation reaction. So 3 sulfur dioxides plus water goes to elemental sulfur plus H2SO4 plus 2 oxygens. And it's that acid that causes the most intense alteration. And then the second stage of weakly acidic fluid incursion, including a meteoric water component from which the rest of the sulfides and the precious metals, together with euhedral quartz, will precipitate. So it's complicated. Now, that lecture, that Australian lecture, used the word lithocap, which is you see that word a lot. The lithocap is what forms as a result of intense acid leaching, which generates vuggy silica to quartz alunite and to more distal kaolinite. So that is often called a lithocap because it sits on top of often porphyry copper mineralization. So there you can see this is sort of the primary mineralization down here, primary alteration, then sitting on top of it is what happened as a result of the reaction of this stuff with the groundwater and the atmosphere and probably biology too. So here you can see this is in Iran. Here you've got advanced argillic alteration exposed in this stream cut. And then here's the remnant of the lithocap sitting on top of it. So if you're out exploring, you're going to be looking for lithocaps. And as I recall, Matt, we talked about the term GEOS being equivalent to lithocap, except GEOSs are applied to VMSs and lithocaps are not, right?
Yeah, it's not usually called a lithocap on a VMS, no.
But the processes of formation are very similar.
Very similar, yeah. So Gaussins are dominated by iron oxide minerals, silica, alunite, jarosite, things like that. So these bodentite, these sulfate mineral, low pH sulfate minerals.
So the next section that we have is low sulfidation epithermal gold systems. I thought we just covered that. Maybe no. So that low sulfidation epithermal gold silver deposits are documented worldwide as structurally controlled veins or hydrothermal breccias, representing major upflow zones for hydrothermal or geothermal systems. So these are typically hosted by calc-alkaline or alkaline volcanic rocks. And here we have an example. This is Cripple Creek in Colorado. And that is a very good example of a low sulfidation epithermal gold deposit. So here's what it looked like 35 million years ago. So we imagine that there was a volcano, some igneous plutons underneath it. And obviously there's the epithermal environment. And here's the, we haven't really talked about mesothermal, but Matt, maybe you know something about that you could add to what the hell that means.
Well, it just means deeper. So you've got epithermal and mesothermal. Yeah.
So mesothermal.
Yeah. Okay.
Yeah. Okay. Now I got it. So this is very shallow. This is significantly deeper. And then obviously within here, there must be low sulfidation and high sulfidation. So I imagine this area is more high sulfidation, but it's underlain by the entire thing's underlain by the batholith, so I'm not sure that's true. But you can see that the mineralization is quite shallow, you know, in this epithermal. Cripple Creek being low sulfidation epithermal. So, you know, Cripple Creek was a very important mine. It's more than 24 million ounces of gold were recovered, and mining to this day produces roughly 250,000 ounces a year. So good company if you own it. So here we see some examples of the rocks associated with low sulfidation epithermal systems. So there's lots of different textures, crustiform banded quartz and chalcedony veins, cauliform laminated chalcedony, Druze lined cavities, lots of very interesting ones. These are from New Zealand. There's one with banded quartz electrum sulfide assemblages, and there's one with high grade, low silicification epithermal gold silver, and this is silica sinter, which forms around hydrothermal deposits. So, you know, we were exploring what is the difference between a Carlin type and a low sulfidation gold deposit. And, you know, this one is, you know, Carlin type golds are characterized by their sediment hosted environment, presence of invisible gold in both arsenic rich pyrite and arsenopyrite. These formed by hydrothermal circulation up to 300 degrees, which mobilize the gold as a sulfur complex. And the gold in Carlin type deposits is typically found in silty carbonates, not obviously related to a volcano. And they're associated with other elements. Low sulfidation epithermal gold deposits formed by fluid boiling caused by a drop in pressures as hydrothermal fluid approaches the surface. These deposits are associated with the nearby volcano and are characterized by a fluid that's usually crystal clear and has a neutral to slightly alkaline pH, often containing significant silica, other things. And the boiling point is critical for gold deposition in the low sulfidation. So you can decide for yourself whether or not Carlin type gold is, how closely related it is to a low sulfidation epithermal deposit. So epithermal gold silver deposits share similar tectonic settings with porphyry, gold, copper. usually forming in continental, island, and more rarely post-collisional arc settings. And the low sulfidation epithermal systems are typically preserved in young and immature arc settings where you haven't gotten the erosion down to perhaps expose the porphyry copper. So well-endowed porphyry copper belts, such as the Miocene of central Papua New Guinea and the Eocene-Oligocene belt of northern Chile, are not prospective for these kinds of deposits because any of the overlying low sulfidation epithermal systems would have been eroded. So that's a link between some of our mineralizing systems. Okay, now we're going to switch gears completely. We're going to talk about placers. So placers are basically, make the gold somewhere else, erode it, concentrate it mechanically in, a stream bed or whatever, and go find it, right? So placer is a Spanish name for shoal or river deposit. And I think we all know something about placer deposits because, when you're seeing those old pictures of old prospectors panning for gold, they're working the placers. So here we can see there's 5 types of placers that we're going to talk about. There's alluvial, which is transported by a river. There's colluvial, which is transported by gravity action down a slope. There's eluvial, which is material still at or near where it was eroded. There's beach plasters, which we've talked about quite a bit. And there's paleoplasters, like the Witwatersrand, perhaps the most important gold deposit in the world. So the California gold rush of 1849 started with individual placer mining. And you can see, if you're gonna do hard rock mining, you're gonna need money to buy equipment and pay people, to do all the things. But if you're just placer mining, you can do it by yourself if there's enough of it there. That was California's Diamond Jubilee 100 years ago. And here you can see 1852, our very woke miners here using a sort of a different way of isolating the gold. All right, so placer gold forms as a result of the weathering, mechanical liberation, and transport of pre-existing gold deposit. And it really requires the fact that gold is fairly chemically inert, so it's not going to be dissolved and carried away for the most part as dissolved load in a stream. It's going to be the rocks that are going to contain it are going to get broken down, and you'll start off with something like this, and that will be liberated, and you'll end up with nuggets and then maybe dust. And in some humid and tropical environments, such as Papua New Guinea, you can get gold-bearing conglomerates can reach as far downstream as 40 kilometers from their deposit source. So this brings us to the world of they call it artisanal gold placer mining, but there's a lot of poor people in the world that are trying to figure out how to make a living, and many parts of the world, gold mining of placer deposits is quite accessible to these communities, and that's a lot of what happens in very poor parts of the world. So these are ASMs, artisanal and small scale miners. So you can see, there's a lot in China and India, but it's been estimated that about 20 million people in the world are dedicated to artisanal mining for placer gold, which is about 40% of all artisanal mining is working on placer gold. Let's see if we can get this going. I wonder why I won't. So I'll end my show. Sometimes that brings it back.
In our daily life, most of us come in contact with gold. We wear gold, use gold, or buy and sell gold. About 20% comes from artisanal and small-scale gold mining operations. These operations provide a livelihood, either directly or indirectly, for an estimated 100 million people in more than 70 countries, putting food on the table and paying for necessities like school fees. But due to a lack of awareness or alternatives, many of these small operations use toxic mercury, an ancient technique, to extract their gold. We know that mercury-free technologies are more efficient and produce more gold. When miners are able to use these technologies appropriately, they are safer and more productive. This also gives miners better access to formal markets that require responsible production. Planet Gold was created to bring the miners together with those who can improve their operations, their health, and the global environment. We are working with countries all over the world to integrate miners into the formal regulatory system, to help miners access new financing opportunities, to introduce mercury-free technologies and training that enable them to produce and sell more gold, to help provide for their families and their communities. We believe that when miners are able to operate responsibly in the formal economy, artisanal and small-scale gold mining provides decent, well-paying jobs, reduces poverty, and promotes sustainable development, all while creating a global supply chain of gold from small-scale miners that is safer, cleaner, and more profitable for everyone. To learn more and find out how you can make a world of difference, connect with us at planetgold.org.
All right. So, and one of the techniques that we use in exploring for minerals, not just gold, but any kind of deposit, is stream sampling. And that's kind of a placer study. So here we can see, here's a pit, you know, and it's got 196 parts per billion of this. I'm not sure whether it's gold. Yeah, it's bulk leach extractable gold. And then if you stream sample, you see 15 parts per billion, 7 parts per billion, 2 parts per billion. The way they found this deposit was stream sampling, and they found 7.4 parts per billion in the stream samples. So basically they just said, well, it's got to be up this stream somewhere. And they basically, it allowed them to focus their studies. And stream sampling is very popular, very effective way to explore very large regions. Now, Matt, you know more about this than I do, I imagine. You want to add any comments about this?
Sorry, I was focused on something else. Sorry, I apologize for that. So
no, we're just talking about
stream
sampling and how it can be very useful for finding new deposits.
Oh yes,
as kind
absolutely.
of a placer mining of you know, you're not after what you found, you're after the information it gives you.
Yes, I mean, well, stream sediment sampling is highly effective for deposits that are close or near surface, close to or at surface, somewhere up the catchment. And you don't know where. So you follow, once you find an anomaly in a stream, in other words, you find excess amount of gold or one of its pathfinders, you can then track that back up the catchment to find the deposit.
Yeah. And then you start drilling, and then you
start drilling.
Yeah.
Yeah.
So cool. Yeah. So I figured that was a good place to stick that in as anywhere.
Yeah.
All right. Now, placer, what's that?
I was just going to say, I was lucky enough to take a geochemistry course at New Mexico Tech in an old gold district in the San Mateo Mountains. And we did that. We sampled, made a pattern and just sampled throughout. And we're looking for completely invisible amounts of gold. And interesting thing is, while we were testing, they said, you know, if you've got gold fillings, don't bite the sample. You're going to mess up the geochemistry.
Good point. All right.
Well,
So go ahead.
can I just jump in there?
Yeah,
Yeah.
but
So actually, the analytical companies now have detection limits so low for gold. I had I was advisor on a project where people had done a soil sampling campaign for gold, and they found an anomaly on every second line of the survey. Right, so one line would have no anomalies, and the next line would have gold anomalies, and the next line would have no anomalies, and the next line would have gold anomalies. And it turns out someone was wearing a wedding ring. And the detection limits are so low that even just wearing a ring while you're sampling will mess up the survey. So cautionary tale.
That's great. That's a great story.
So,
But I mean, it's
so
the
don't
fact
get
that it was
married,
every
kids.
other sampling site gave it away. It's like this is noise, not signal. And who's wearing the wedding ring?
Well, because I asked them how were the lines sampled, and it was like, well, this guy sampled this line, and this one did this line, and then they moved over two lines, and then they moved over two lines, and so it was systematic. So it was one person.
Yeah, that's great. Yeah, that's just poor training. Somebody should have said, and whatever you do when you're doing this, don't wear any gold. But anyway, once we understand how placers form, then we can talk about paleoplacers, which are just placer deposits that have been preserved like any other kind of sedimentary rock. So some of these are really interesting. So this is kind of the biggie, the Witwatersrand paleoplacer. So this is in South Africa, right near the Bushveld. Now, here's the Vredefort Dome, which is an impact structure that is there. So, this is a big area that for some reason they don't have a scale bar. But there's Johannesburg. Where's Johannesburg? There it is. So Johannesburg was cited to be close to the gold fields. You can see how many gold fields are near Johannesburg. So, that's why that city developed there. So, the book doesn't explain what is the difference between a placer and a paleoplacer, but I think it's pretty obvious. If the process that made the deposit is still happening, like if the stream's still flowing, it's a placer, and if it's not, then it's a paleoplacer. So so there's two giant Precambrian paleoplacers. One is the Witwatersrand, and the other is the Tarkawa Basin of Ghana. That's misspelled. And then there's some in the Huronian supergroup in Ontario, and in Brazil, are paleoplacer deposits. So let's talk about the one that I know best. We talked about these streams coming off of the Nevada Plano in California. So this just taking us back to 40 million years ago or so, when this region was high and these rivers were flowing to the west across what is now a mountain range. So, here's the Carlin is up here somewhere, near Elko. Here's the Paleo Divide in the Eocene when the Nevada Plano was at its biggest. And then these are the drainage systems. These are very well documented. You can't miss them. But then there's some others that have been suggested, from various lines, and you get a feel for what must have been a remarkable drainage system. But it's these ones, the paleoplacers of California, that we're going to talk about. So here we've got sort of an outcrop. You can see this on the freeway that goes across the Sierras. And what you're looking at here are the auriferous gravels. That's what they call them, the gold-bearing gravels. These sedimentary, they're not rocks because you need a shovel to sample them, not a hammer. But the age of it is pretty well known because you've got this ash flow tuff, which is 31 million years old. That's Oligocene. So you don't really know the exact age of these paleoplacers, but you know it's older than 31 million years ago. Someone had their hand up.
Yeah, me.
Oh, go for it.
Right. When you're talking about the Nevada Plano, I don't know if I was in on the first of it, but I've seen some studies of zircons that indicate there was flow from that high point down all the way to the Gulf Coast.
Oh yeah, no, that was an interesting result of a detrital zircon study that UT Austin did, as they saw all of these, zircons are made crystallized from granitic rocks. So if you find a zircon of a certain age, that means there must have been a granite at some point. And there's a lot of Jurassic and Cretaceous detrital zircons in there. And there's no Jurassic or Cretaceous granites in this part of the United States. It had to come from Nevada or California. So it was an unexpected.
Next time you go to Padre Island, take your gold pan.
Yeah. Well, yeah, that's an interesting point. I'm not sure if you'd find any, but okay. So that's the auriferous gravels. This topography is erosional from when they were mining it. So here's the auriferous gravels of California. There's the state line, Lake Tahoe, Sacramento State Capitol. There's the valley. These are ancient rivers. So these dashed lines are the tertiary Yuba River, where they're well preserved. There's a town called Placerville, so you can imagine why that was named, right? And so there's quite a few of these tertiary river channels. And what happened was, so here is the present bedrock. Here's the present river. And then back in the tertiary, there was a channel that was up here, and then it was covered by lava. So that basically meant that the drainage had to go find a different place. So these things are sort of inverted topography. Well, what was originally river valleys is now the tops of ridges. So most of the gold is at the bottom of the paleo channel. So here's a schematic tertiary channel. So this is the lower or channel gravels. Then you got the upper or bench gravels, and then you've got some rhyolite tuffs and interrhyolite channels. And so what they do is they drill through this in this one site, and this is the distribution of gold that they found. The lower gravel's got a lot more gold than the upper gravel, right? And that's getting close to a part per million gold, which was quite a bit more than they're mining in the Carlin. So you're going, why aren't they mining it now? It's like, okay, we'll get into it. Okay, so this is just showing these channels again in a different way. These are the big ones that were attracting the attention of the 49ers. And this is the problem, is this is how they mined them. So here, these are called high pressure, these are called water cannons or monitors, and they would just bring in the water and just blow it at the hillsides and then get the runoff and capture it there. And that's sort of what it looks like. This was what it looked like when it was actually being mined. This is what it looks like today, kind of a badlands. So it started, this one mine got to start when the prospectors found gold in a small creek, especially other people found it, and they ended up calling it Humbug Creek because they didn't find as much gold. But then they found it in gravel piles, and the hydraulic mining that we just saw began in 1853. And by 1857, it grew to 500 people. So this French immigrant saw the potential of the mine, bought plots all up and down the region, and then he scaled up every aspect of the mining operation. adding 4 monitors that could blast 25 million gallons of water a day, built 100 miles of dikes and canals to deliver the water. And one of the biggest project was the one that caused a lawsuit, was the creation of a 7,800 foot long Bloomfield tunnel, which would send debris into the South Yuba River. So by 1876, the mine was fully operational with 11 reservoirs, sending 100 million gallons of water a day to the mining site to move over 100,000 tons of gravel every 24 hours, and North Bloomfield grew to 2,000 people. Well, so this is kind of the situation. So, you know, the Bloomfield is here, and the town of Yuba City is here. And back then, you would get riverboats would come up from San Francisco to the head of navigation, which was for the Yuba River was Yuba City. And yes, Clint, you had your hand up.
I was just going to say that the musical "Paint Your Wagon" is actually a documentary.
Oh, really? Of the Placer, you know?
Well, not so much of Placer's, but just of the whole, you know, the whole schmear.
Oh, okay. I'll have to watch it. All right. So increased production would come at a cost, as the debris from the mine would raise the riverbed of the Yuba and Sacramento rivers above their banks in some areas and cause flooding. And the town of Marysville, as well as the city of Sacramento, experienced flooding due to the rise. And here's we got an example of what it looked like, you know, all of the debris going into the river. So following a series of floods, Marysville farm owner and business owner Edward Woodruff filed a lawsuit against the mining company in 1882. And basically the claim was the debris has filled up the natural channel of the Yuba above its level of banks surrounding country. Also the Feather River below the mouth of the Yuba to be depth of 15 feet or more, buried with sand and gravel, destroyed all the farms of the owners on either side of the Yuba. And the lawsuit in 1884, they concluded that the operation of the mine was destructive to those downriver and banned debris to be washed into water sources. And then the California legislature passed the Sawyer Act, which ended hydraulic mining operations across the state. Let's see if we can get this one going.
If you've ever wondered what the inside of the Sierra foothills look like, it's this. In a way, it's beautiful. A kaleidoscope of sedimentary rocks piled up layer on layer. But this spot, this massive location, has an ugly past.
When they had it at full operation, you're talking about 100,000 tons of material a day that was getting blasted. We're talking about mountainsides just completely blown away.
This is Malakoff-Diggins State Park. It's located in Nevada County's remote town of Bloomsfield, and it's the site of one of the most destructive mining operations in California history.
And what you have here is an area that was carved out by hydraulic mining through the use of large monitors, which are basically these huge water cannons.
Miners use those water cannons to extract gold from the mountains. Park Supervisor Dustin Patterson says it's a process known as hydraulic mining.
You just fire this thing off and at 16,000 gallons a minute, it's taking that hillside out completely and in no time flat.
Hydraulic mining is extremely destructive, but not only to the environment, but to anything or anyone downstream.
Downriver in the actual valleys, we had farmers that had their fields flooded, we had towns get destroyed.
Hydraulic mining at Malakoff got so bad, it prompted the very first environmental lawsuit in California.
In 1884, the Sawyer decision essentially banned hydraulic mining by banning the discharge of the gravel and sediments into local water courses.
Not long after hydraulic mining was banned, the town of Bloomsfield went bust, and Malakoff-Diggins mine was abandoned. How long is it going to take for stuff to grow back here?
That's a great question. As a rule of thumb, topsoil takes years, hundreds of years to accumulate.
More than 130 years later, the rusty metal pipes still litter the 3,200-acre state park. They act as a reminder of how destructive gold fever can be.
This will be fixed over time, but in my lifetime, your lifetime, our kids' lifetime, this scar is going to be here.
Here at Malakoff Diggins, it's a place to learn about the environmental impacts of man. What is that loud noise that we're walking up on here?
That is the generator that runs the park right now.
Ironically, a polluting diesel power generator has been powering the park since they took ownership in 1965. But that's about to change. By the end of the year, Malakoff will become the first state park in California to be completely solar powered.
Remembering our legacy of hydraulic mining and the environmental damage, we've gone from it being an environmental disaster to being part of the environmental solution.
From the water-stripped mountains of Malakoff Diggins State Park, I'm John Bartel. Hope to see you on the back road. Hey, thanks for watching, and check out some other videos just like this one. Also, subscribe and write in the comments and tell me where else I should be checking out.
Producing district in the world. It was deposited between 2.96, 2.71 billion years ago, so in the Archean. And it's produced over 2 billion ounces over a century, at an average grade of 15 grams per ton. Still reserves of more than over 1 billion ounces of gold. And this is basically a conglomerate. And, so what you've got here is, you can see the white quartzite cobbles. And so this is a 8 by 10 centimeter photograph. So those are good sized cobbles. And the matrix is chlorite and auriferous pyrite. So it's that gold bearing pyrite that's of interest. And there's other things in there too that testify to Earth's interesting environment, including uraninite, which is normally not preserved as a mineral. Yes, Clint?
I was going to say, Doc Manton was talking about some of the really, really old clastic rocks like this have, over time, I mean, they're like, 3.5, 4 billion years old. They have like just no porosity whatsoever. So they're super hard rocks.
Yeah, that's certainly the case. All right, so this is kind of the sketch that has been offered for how the Witwatersrand paleoplacer formed. So you can see there's some kind of an alluvial fan and braided gravel bars, and there was no life to constrain these streams. So that's kind of how it's imagined. Not that different than the California paleoplacers. And sort of this is showing, let's see, I think over here we've got, this is the Bushveld. Now the Bushveld's only 2 billion years old, whereas the Witwatersrand is 1 billion years older. And the gold bearing horizons are often called reefs. So these large Archean sedimentary basins that are this well preserved are rare. And we already noticed that the main gold fields lie up in the north near Johannesburg, quite a few. And 8 of the world's 10 deepest mines are in the Witwatersrand. So about 4 kilometers depth limit is the limit of for human mining. So this mine is the deepest one at 4 kilometers. And what happens is the rock gets so hot, and the only way they can deal with this is to pump in slurry ice to cool air below 86 degrees Fahrenheit. And then they line the excavated areas with cement, to help. But you've also got problems with rock bursts, which is always a problem when you get deep underground. And it kills about 50 South African miners annually. And just there's whole engineering, you know, challenges related to mining this deep, but obviously it's worth it. Another one is Tarkawa in Ghana. Ghana is a big gold producing place. It's down here in the south. And, you know, it's sort of in this area. Oh, there it is. And it's a sedimentary basin. And this is the much younger than Witwatersrand. It's 2.1 Paleoproterozoic. So this is kind of the depositional environment that people see that they interpret for the Tarkawa. And then this is the stratigraphic section. This Tarkawa group's about 2 or 3 kilometers thick and strongly deformed. And this is the pit. So there's 4 large open pit mines. Because it's so deformed, they sort of mine long, skinny pits, not round ones like we often see.